So let's go on to the next speaker, Pedram Khalili from UCLA. He's going to tell us about MRAM. His co-author is Kanwan, and they have made some terrific progress on a novel switching mechanism for MRAM called on the basis of voltage-controlled magnetic anisotropy.
Okay, good morning, everyone, and thank you, Jeff, for the introduction. And I would like to thank the organizers for the invitation. It's great to be here and share some of our work on electric field-controlled MRAM with you. So this is the outline. I'll briefly go over the motivation, why we think electric field-controlled MRAM is interesting, mainly from energy efficiency perspective, since that's the focus today, but also from density point of view, which is very important for memory applications. And then I'll go over the device operation and some of the device data that we got. So, okay, so the idea to use magnets to store information, of course, is not new. Half a century ago, we had something called core memory. Hard disk drives use magnets, obviously. And then spin-torque MRAM in recent years has gotten a lot of attention. But what all of these have in common is that they're essentially current-controlled devices. To switch magnetization, you use a current, which generates either a magnetic field or spin-torque or whatever mechanism. But generally, whenever you have current and you're passing current through a resistive device, there is ohmic energy dissipation, which is something that we want to basically reduce or eliminate. So that is basically the value proposition for magneto-electric RAM. So you can basically construct a sort of a table here. Oops. And compare basically the main production process memories to those which are in development. And in terms of energy per bit, what we have measured, and I will show in a moment, is that, in fact, we have more than a 10x advantage compared to the next best thing. But also, equally importantly, and I will come to that in a moment, density is a big advantage also. And that's very important because one of the markets that MRAM is trying to get into but has not been very successful so far is DRAM. Then also endurance is very important. Any application where you need frequent memory access, frequent writing into the memory has to have high endurance. And a lot of emerging non-volatile memories have trouble with that. So that's also an inherent advantage. So overall, we think that the package, as a package, it is very compelling. Obviously, there's challenges that we need to get to large enough densities for this to be interesting. But so in terms of energy efficiency, what do we mean when we talk about energy efficiency? One is static power dissipation. And as the previous speaker elaborated on this, when you have magnetic memory or magnetic-based technology, it's inherently non-volatile. So that eliminates the standby power dissipation, which is very interesting. But also the dynamic power dissipation is important for, at least for some applications. This is one example where some of our colleagues at UCLA did an analysis a few years ago. They were looking at adders, basically where it's a CMOS adder, but it has some magnetic tunnel junctions embedded in it. And basically, it's meant to store the information as it goes along so that you can power it off when you're not doing computing. But it turned out that the overall energy efficiency of this was limited by the dynamic power dissipation of those MTJs. So they consume too much power if you use spin-torque, which is current-controlled mechanism, to switch them. The point about density is equally important, especially for high-density memories like DRAM. And you can basically see why by looking at this sort of 2x2 array cartoon that I have here. It's a 1T1R, one transistor, one resistor kind of array. But as it turns out, basically, in order, if you need currents to switch the magnetization in these MTJs, basically those currents have to be driven by these transistors here. So what that means is that those transistors have to be fairly wide if the switching current is large. And that is the case for spin-torque MRAM. So in reality, what limits the density of your MRAM will not be how small of a magnet you can make. It will be what the switching current is and what basically the transistor size is. And if you, from simple analysis, you can see that actually that situation gets worse as you scale. So you will not be able to get the full benefit of scaling in terms of density. So for all of these reasons, we think that looking into new ways of switching magnetization, particularly electric field control, is interesting. So how do we go about that? There's several ways of making electric field controlled memory, and many groups are working on this, including at UC Berkeley. The one that we are working on is very close to existing MRAMs. So it has still a magnetic tunnel junction structure, and that's important to be able to read out the information. So we have a reference layer and a free layer which can switch either up or down. And then based on the resistance, you can basically find out what state the information, the bit is in. Now, we use perpendicular magnetic tunnel junctions because for small devices below 50 nanometers or so, that's the only way to get large thermal stability for retention. But the important thing is that the perpendicular anisotropy here is a function of the electric field that you apply across the MGO layer. And so you can basically, there is basically a voltage-controlled magnetic anisotropy, or VCMA for short. So you can parameterize that in terms of units of, well, change of surface anisotropy as a function of electric field. And then you come up with a number which is typically in the tens of femtojoule per voltmeter. So the details are not important, but basically the message is that you can control anisotropy by voltage, and then we're trying to switch the magnetization with that. So there's two ways of doing that now, two ways to switch the magnetization. If you can control anisotropy, that means you can control the energy barrier between the two free layer states. So one way to switch then is you just reduce the energy barrier and you wait for thermal activation to switch the free layer. So that works, but as it turns out, in order to get bidirectional switching, in order to be able to switch back, then you need a changing external magnetic field. So that's not great, of course. There's ways to do that in an array, but it would be nicer if you could have a constant bias field or no bias field at all. And so that brings us to the second way of doing this, which is precessional switching. So here, basically, what you do is you have the same structure, essentially, but you apply a somewhat larger voltage. And this larger voltage now eliminates the energy barrier between the two free layer states. So what it does is it tries to reorient the magnetization from the perpendicular direction into an in-plane orientation. But this being a magnet, it does so through a precessional motion. So it basically starts precessing around the in-plane direction, which means that if you turn off the pulse at the correct time, it will end up 180 degrees from where it started. Right, so you can get a full 180-degree switching with this. The caveat is that it will switch regardless of where it started. So you need to do a read before you do the writing in order to basically find out if a write is required. Now, this works very well. So this is basically measurements from a 60 by 60 nanometer device. And so basically what we do here is we measure the probability of switching for different pulse widths and pulse amplitudes. And you can see that basically the probability has sort of an oscillatory behavior as a function of pulse width, which exactly shows you that this precessional kind of switching is happening. Then you can do basically some more device optimization, and you go from this kind of device, which does switch, but it doesn't get quite to 100% switching probability, to something like this, where you have a fairly wide write window of about half a nanosecond, where you have 100% switching probability. And these write windows are really important. It's important to have a wide write window. The reason for that is to be able to account for variability from device to device if you go to larger numbers of devices. So that works, and then you can make arrays and measure basically statistical distributions and so on. But one of the interesting things that we noticed when we started basically looking into making arrays out of these was that there is a sort of a additional advantage if you use VCMA. And that is, again, in terms of density. But basically, where this comes from is that VCMA-based switching is inherently unipolar. So what I mean by that is that you only need one polarity of voltage in order to switch, unlike STT, where you need basically different directions of current in order to switch in opposite directions. Now, the result from that is that you have a lot more flexibility in terms of what kind of select device you use for the memory. So you can use, for example, a simple Schottky diode, and then you can have basically a crossbar kind of architecture for MRAM, which, again, doubles the density compared to the 1T1R, which I showed you a few slides back. So there is basically, and this is, again, important for a lot of memory applications where basically the cost per bit is directly determined by how many bits you can put in unit of area. OK, so how low energy can we get with this? So basically, that relates to scaling. And so here we compare a number of devices going from 100 nanometer in diameter all the way down to about 50 nanometers. And you can see that basically the switching energy scales very well. So it goes down to around 6 femtojoules or so per bit for a 50 nanometer device, which is easily at least 10 times lower than a current controlled device. Even though this is not current-induced switching, you can also, just as a benchmark, look at the current that's passing through the device during the switching. And that turns out to be around 6 microamps in our case for a 50 nanometer device. And importantly, this is for very fast switching. So this is around 600 picoseconds or so. So for those of you familiar with MRAM, you will know this is basically impossible to get with current-induced switching. Another interesting feature is basically if you look at the thermal stability, essentially the energy barrier between the two free-layer states. And the reason that we look at this is you have to make sure that you're making a fair comparison as you scale, right? So you want to compare the switching energy and switching voltage and so on between devices that have the same retention time. Now, naively, one would expect that as you scale the device size, if you have a constant perpendicular anisotropy, that you would have to, because the area is becoming smaller, the retention time would go down. Now, as it turns out, that's not really the case, down to a size of about 50 nanometers or so, which is the smallest that we have shown here. As it turns out, this is something that folks working on spin-torque MRAM had realized a couple of years back, or maybe a few years back. And it's called sub-volume activation. So basically, what that means is that for sufficiently large devices, larger than about 30 or 40 nanometers or so, even though the standby condition of the device is single domain, when it comes to thermally activated switching, essentially there is a lower energy path, which is non-uniform. So it basically goes through sort of a magnetic texture, which is smaller in volume than the volume of the entire bit. And that results in the thermal stability then being essentially independent of the device size. Over this, again, down to around 50 or 40 nanometers or so. But that's sort of, it's kind of a good thing for as long as it works, because basically then you don't have to worry about increasing perpendicular anisotropy in order to increase the thermal stability. But interestingly, for VCMA, it also affects the VCMA switching, because essentially what you're doing when you're using anisotropy changes to switch a magnet is that you're changing the energy landscape in the free layer. And so I will not go into the details, but basically what it comes down to is that also the switching voltage turns out to be essentially independent of the junction diameter, at least down to 50 nanometers or so. Now, my last couple of slides are sort of looking forward into the materials requirements. And so basically, we want to go to lower energies, lower switching voltages. And also, in order to scale, you would eventually want to have larger anisotropies. And you have to make sure that those anisotropies also remain sensitive to voltages that you apply to the device. So what that means is that the VCMA coefficient, basically the sensitivity of anisotropy to voltage, has to go up. In addition to that, TMR is also important. So whatever you do to increase the VCMA, you have to make sure that the tunneling magneto resistance also remains high and, in fact, goes up if you go to larger arrays, because it has to be able to account for device-to-device variations so that you can do a reliable readout. So how do we increase VCMA? So if you look at this basic structure, there's at least two things that you could do. One is you can change the dielectric layer, for example, using the high K dielectric. And you would expect that the voltage sensitivity would go up. However, you have to make sure that the TMR does not suffer. The other one is that you can change the metal seed and cap layers next to the free layer. And that also turns out that it affects greatly the VCMA, the TMR, the temperature stability, everything. But just to show you one of the recent results, and this is work that we've done in collaboration with Jane Chang's group at UCLA, is we developed a high K dielectric. Basically, it's a composite dielectric which has a high dielectric constant. And the idea here was to increase the VCMA while trying to also have large TMR. And you can see that we sort of succeeded in this. So we see a 40 to 50% or so increase in the VCMA coefficient. Of course, the starting point was not great, but that's for other reasons. But we do see a consistent increase, which shows that basically the idea of using high K dielectric works. But more importantly, the TMR does not suffer too much either. So it goes from around 60% to 50% or so. So this is encouraging. It's not yet product quality, because for any sort of reasonable density, you would need 150 to 200% or so TMR. But it's a good first result, we think. So this is the summary slide. I will not go through basically all of these item by item. I'm almost out of time. But I would like to thank you for your attention, and happy to take questions.
Okay. Do we have any questions? Oh, yeah, go ahead.
I'm just holding the mic.
Oh, you're just holding the mic. Okay. I'll ask a question. I'm not sure I followed completely the argument at the very end there about scaling. It sounded like you were talking about scaling the amount of VCMA to affect the switching energy. But as you showed in your plot, once you scale below about 40, 50 nanometer in size, the energy barrier starts to shrink, so your retention time suffers. So, of course, in the STT-MRAM world, they're looking towards higher coercivity magnetic materials. Now, how does that come in for VCMA? Are there what is known about VCMA for some of these higher coercivity magnetic materials?
Yeah, you're quite right. So when you go below 40 nanometers or so the subvolume activation does not help anymore. Basically, the retention time would go down if you stick with the same materials. So you need larger PMA. You also need larger VCMA now, because you need to be able to change that larger anisotropy. So there is quite a bit of work looking at different materials. Iron palladium, iron platinum, those kind of materials which are known to have large PMA. But really the tricky part is to get the combination right. You need large PMA, large VCMA, as well as large TMR. Yeah. So it's still an open question, basically, what material could scale sufficiently below, let's say, 20 nanometers or so.
Yeah. Okay, good. Go ahead, Eli. Eli gets one question for each speaker.
Yeah, only the interesting speakers, right?
So far, every speaker's gotten a... Don't say that, because then you'll insult the speakers if you don't ask a question.
So I think when I think of magnetism, I think of current control. Yet you're talking about voltage control. So if it's going to be voltage control, it has to be a very low voltage. And I don't recall that I saw how low the voltage would be.
Yeah. So the voltage numbers are not there. But typically, the switching voltage is around maybe 1.5 to 2 volts in these devices. It's not very low. But it comes back to basically how large of a VCMA coefficient you have. If the sensitivity of the anisotropy to voltage is increased, the switching voltage would reduce by the same factor. And that's part of the reason that we're doing, in addition to scaling, part of the reason that we're looking into increasing these VCMA parameters. So this is a low power memory, but not a low voltage memory.
Okay. One more?
Well, can I just quibble with that?
Let's give somebody else a chance. Go ahead.
You mentioned a high K dielectric
We'll
in the
have time for
MTC
the
cell. So what kind of high K are you talking about here?
Well, I didn't mention the material, but the K is around maybe 2 to 3 times larger than the MGO. So it's not super large, but it's relatively large.
Okay. Thanks, Pedram. Let's thank Pedram again.